Taught at the Astro 101 level are taught in lecture only. There is no breakout section, there is no recitation, and there is no lab. So it's a really tricky environment. It's the universe in a semester. Go. And you have no thing but lab to work with. So what do you do in that environment becomes one of the interesting things. And I'm going to talk about some of the techniques. This is just a list of the collaborators in the CAT's national program, and you're not intended to read it all, but I just want you to realize there's a lot of people working together to solve many different fundamental research questions that they have motivated to try to solve. In many ways, this is a collaborative group of my graduate students right now, because they work in clusters of 5 and 6 on different research projects that they publish their results in journals. I'm going to take a moment to give you a very quick lecture. It's very important that you learn about traxylene. Turns out traxylene is a new form of ionomer. And what's really interesting is the Sarastonin engineers have figured out how to crystallate large amounts of febron in the process of bractering and quasarine traxylene. Now, I've talked about in this class before that process is important, but also the nature of how it relates to your everyday life. It turns out that traxylene may be one of our most listed sausages, and that's simply because of its ionomer. Obviously a crap lecture, right? Obviously nothing reasonable or scientific or real in any word I just said about any of those things. Did you ever feel like that over the last 2 days? Be careful with our language. Might be the first lesson that I give anybody when we talk about the nature of engagement, teaching, conveying understanding, developing discourse in a common language. When we think about the charge that this meeting places on ourselves and moving astronomy as a vehicle into teaching physics, I caution us greatly about our use of language and our assumptions about what one field understands about another discipline. Because there's a lot of terminology in astronomy, and some of it was getting thrown around pretty cavalier and easily. And I think we need to be very, very careful there. I think as we talk together, defining terms and looking for the term that is a common term we could all use, that doesn't require an astronomy background, vernacular to be able to use in a physics classroom will be one of the important things for us. So I'll just use this quote to kind of bring that back. Lectures often been described as the process of taking information contained in the teacher's notes and transferring them to the student's notes without that information passing through the brains of either. So I just throw this up there as one of the frameworks about what I'm talking about when I say we need to move away from traditional instructional methods to active learning methods and intellectual engagement that happens when you leave lecture and put the onus of learning on the student's shoulders and create interactive engagement strategies which force you to reason and think deeply about the ideas that you might have presented in the lecture. So I'm not saying lecture is not a valuable tool. I do it every day in my class, but in limited amounts for very, very particular reasons to make very small pieces of information that you need to then go further in the student engagement parts of the class. From the book, How Humans Learn, a great book that distills many different disciplines. Humans are viewed as goal-directed agents who actively seek information. I continuously try to tell myself that's how I'm supposed to view my students. They come to the formal education with a range of prior knowledge, skills, beliefs, and concepts that significantly influence what they notice about the environment, how they organize and interpret it. This in turn affects their ability to reason, remember things, solve problems, acquire new knowledge, and if students' initial ideas and beliefs are not acknowledged in any way, it significantly changes what happens later, what they actually learn, what they're able to do. My goal in teaching is to pass on culture, to help them understand the nature of the discipline, to create active agents in society. I want the students who leave our classrooms to go off into society as ambassadors who can't help themselves, but talk about our discipline and share it with others. If we want to have a solution to what we call our STEM pipeline problem, we're going to have to do a lot more than have better lectures and clever problems at the end of chapters that people can solve using different algorithms. We're going to have to get out of just that model as the only way we think about the solution pathway. The best lecturers often make the worst teachers. They are, in a very real sense, perceptually challenged. They can't imagine what it must be like to struggle to learn something that comes so naturally to them. I think, again, at this meeting, we have to caution ourselves here again to really realize that the students we're going to work with, whether they're juniors or seniors at the undergraduate level or not, are going to struggle to understand some of the things that we've been cavalierly going through in our talks so far today and talking about different ways in which you understand the physical universe. So I'll kind of try to talk a little bit more about that. Most ideas about teaching and learning are not new, but not everybody knows the old ideas. Euclid. I think that's Euclid. I'm going to talk about some curriculum and models and things, but I want to make this point really clear. It's not as though our understanding of how humans learn doesn't date back to a prior history within Western civilization. I mean, the idea of a mentor and student in a Socratic dialogue is quite old. How it manifests in the modern classroom, though, is quite unique and non-trivial. So we talked about a set of activities that I'm a part of with the Center for Astronomy Education, and they're a workshop series. I'm going to talk about some of the things that go on in the workshop. I'm going to talk about how that affects what happens in the classroom, and I'm going to provide some data and evidence for how it changes the results of classroom engagement and student learning. And I want to make this point really clear. The data I'm going to show is mirrored perfectly in results and research that's happened in physics. So I might be showing you results from astronomy education research, but they are mirrored beautifully in physics education research for the same conclusions, for the same reasons, because they're based on how humans learn cognition. Not because they're couched in one particular discipline or not, but they're generalized to how humans learn. So I'll be talking about, as Kevin brought up, tutorials. I might even show you an example of a ranking task, peer instruction. I'm going to try to model some of that. I might even get into showing you a simulation real quick. There's many different tools that can be brought into the classroom and the learning environment, whether that be lab, recitation, any of those environments, that go beyond what you may have experienced as traditional instruction in terms of lecture and confirmation-based recipe-oriented labs. And that's where I hope we spend a significant amount of our time, is focusing on things that aren't the traditional instruction. Because if there's one thing all this research shows, is these new ways of thinking about teaching and learning outweigh the success of these old ways in orders of magnitude. 2 or 3 letter grades at a time of improvement beyond the traditional methods. And so I hope that as we think about bridging this gap between what we wish to happen in physics by using astronomy as a vehicle, we also bring with that we could be doing things differently than traditional methods of instruction. So, actually, let's vote again. A is, I'm so familiar with this topic that I could probably give a lecture on it. B is, I've heard it before, but it's worth you talking a little bit about it. C is, I've never heard this term in my life. Pedagogical content knowledge. PCK, or pedagogical content knowledge. I'd like you to vote on 3. 1, 2, 3. Well, that's not bad. Okay, excellent. So, just in general, it's your understanding of your discipline, your own understanding of your content area. It's also your understanding of how that world of psychology and education and cognition describes the nature of human learning, the organizational principles of the human mind. It also talks about the understanding and awareness of pedagogy, instruction, assessment strategies. It talks about your understanding of the classroom environment itself, the restrictions that it might imply, the nature of the limitations on the environment, issues related to teaching and learning, and almost, if these were proportionally sized, the largest circle might be those people that you teach themselves, their motivations, their intellectual abilities, how they come to the instructional setting, what they expect to get out of it. Your understanding of how all these things are related to one another is your pedagogical content knowledge. And what you choose to do in the classroom, how you can convince yourself that what you are doing is valid and reliable and worth doing, and why you would choose to do it, determines what will happen in your classroom setting to some extent. It doesn't determine how good of a teacher you are necessarily, but it certainly frames for you what you should be doing in the classroom and why. So I bring this up to say, I hope we have in our minds that we need to be very cognizant about the fact that humans learn in very well understood ways, and that we're working in a particular context that we're trying to bridge with astronomy and physics. So this is a slide that I've been using as of late. Come mothers and fathers throughout the land, and don't criticize what you can't understand. Your sons and your daughters are beyond your command. Your old road is rapidly aging. Please get out of the new one if you can't lend your hand, for the times they are a-changing. There's about 10 points I want to make about what we're doing today that is encapsulated in that quote. We brought up this aged Halliday and Resnick curriculum more than once. There's an irony to me here. I was a Halliday and Resnick student. I brought my Halliday and Resnick book to this meeting because I just won the Halliday and Resnick Teacher of the Year Award at the APT. I'll be thinking there's some kind of irony about all that. And I do agree that it's like a 14th century curriculum kind of sitting there for us each semester. And I think that's important that we realize that's embedded in this book. Along with that is, I've been sitting here already throwing out, we're going to need to think differently than the traditional curriculum. Please get out of the new one if you can't lend your hand. Don't criticize what you can't understand. I mean that we're going to have to be creative. And we're going to have to work at reaching the goal we have won't come through necessarily the most comfortable path you've always walked. This cartoon tries to encapsulate some of this, because at some level, the success that you will have in your classroom is based on your ability to perceive your learners' perception of the content. And so I use this graphic to illustrate this. This is a cartoon that's created to talk about different technologies. How a typical iPhone user looks, how she sees herself, how she's viewed by a BlackBerry user, how she's viewed by an Android user, and that's a picture of Steve Jobs right there. The typical droid user, how he views himself. I love the whole Einstein, it's great. How he's viewed by an iPhone user and how he's viewed by a BlackBerry user. Typical BlackBerry user, how he views himself. That's just the smile, it's great, right? How he's used by an iPhone user, that is a very tired old man. Right? And how he's viewed by an Android user. I'm going to say I have a very dated BlackBerry sitting in my bag. So I know where I am technologically, okay? But how are you viewed by your learners? And appropriately, how are they interpreting your effectiveness in the classroom? If you can't speak their language, if you can't bring metaphor and analogy to their frame of reference, if you can't frame the instructional environment in a way that is obviously profitable for them, you will fail. And it is those things that will make the most success out of what we're talking about, rather than whether or not we choose the sphere of last scatter to talk about the microwave background radiation or and so on. And so I want to bring that to bear as one of the things that challenges us while we're here this week. This is my current classroom. It's the Performing Arts Center at the University of Arizona. This coming spring, I'll have 1,400 students in there. So it's an experiment for me to figure out, can the things we've developed over the last 10 years of working classrooms of 25 to 300 work in a class of 1,400. We just did 2 semesters of experiment with 750. So this is not the entire class. This is just an average day in the classroom. I'm on a stage 4 feet above them. This is where Cats is performed if they come to town. This is half the class. That's not the whole class, it's half the class. When it's 1,400, I'll fill in this section back here. So it's a very strange environment, and the reason I bring it up is what we've learned that has to happen to create an hour and 15 minutes in here for which you only lecture for 20 minutes a day, and the rest is all done through interactive learning strategies, is something I want to make sure that we talk about and share in here, because the learning gains that are happening in this class are at the top of the national average. They're as high as the versions that I had with 150-person classes. It isn't about your lecture. It isn't about necessarily the things that you bring to the classroom that are about the content by itself. It's how you weave that into a narrative they buy into, and how you create an instructional environment that they can buy into. So I'm going to try to give you some examples of that. I also teach in India to Tibetan monks in a program called Science for Monks. And it's a program with the Dalai Lamas where we bring Western science to monks. This is during their neurobiology lecture. There's a neurobiology professor lecturing to the monks right now in full language, like all the language of neurobiology. And there's a poor Tibetan translator waiting to say what the neurobiologist just said, because none of them speak English. That's sort of what I'm concerned about when we make this bridge between the two disciplines, that it feels like that for all our physics students. They're like, right. Nope. This is them in the active engagement classroom. Do you notice a shift in belief system that might have come with it, or attitude, or motivation? One face to the other faces. If you're enjoying the instructional interventions that are being brought to you, learning comes with it. You don't resist. You will try things. You'll take risks. You'll talk to each other. You'll share your internal ideas with each other in ways that are meaningful. And so I just bring that up. I'm going to make you do the same things I'd ask 750 non-science majors to do, or a bunch of Tibetan monks. All I ask you to do is play along. Is that all right with you? Is that all right with you?
Yes.
The first thing you're going to have to do is fill in the blank with your voice when I pause. That's one of the interactive techniques. You're going to have to, and I'll know if you're not, and we'll go backwards, and it'll be embarrassing for you, not me. So let's try it. Let's calibrate ourselves, make sure we can all do this, so that we don't fall asleep and you come along for the ride. You live on the planet Earth. That was almost all of you. Let's try that again. You live on the planet Earth, which orbits the sun, which is a star. Excellent. You're doing great. All the debris, dirt, residue from the formation process that we call planets and comets and moons, all together comprise an object you might call the solar system. There are easily 10 billion or 100 billion of those in a larger scale object, which is all of those solar systems, which is known as a galaxy. Ours being called the Milky Way. So you could look at clusters and clusters of these galaxies. In fact, you could look at all galaxies, all matter, all space, and all time, the thing that I like to call everything, that is known as the universe, which we call the universe. Okay, good. Okay. A little more background before we get going. I just want to make sure we all have the same terms. This is an HBar diagram, Hertzsprung-Russell diagram. It's sort of a significant portion of the toolkit for teaching astronomy. It's a graph. The vertical axis is called luminosity in solar units, so it's all relative to the sun. Good. And luminosity would be a better word maybe at the 101 level, or at talking to human beings level about what that word really is. Brightness. You already have it. Sounds good. Okay, so this is brightness. Up here is bright or dim.
Bright.
Dim. This is the axis that relates a lot of information. I'm going to let you ignore these letters for now, but I'd like you to notice those numbers and that it says temperature. Oh, that was about a third of you. We'll try again. This axis talks about temperature. This end is cold, and this end is hot. I'm going to do that one again because it matters. This end is cold. 90+% of all the stars in the universe exist on this diagram along an area known as the main sequence. Main sequence. This is most every star in the universe would be plotted there if you had all of their properties and you put them on this axis. I want to see if you notice some trends here. The ones down at this end are colored
Red. Blue.
These are big or small?
Small.
With increasing temperature, things get brighter or dimmer?
Brighter.
Are they getting bigger or smaller?
Bigger.
Okay, so you've got some relationships here. The larger the star is, it will also be brighter, and it'll also be hot. Sounds great. It'll also have other properties. What do you think, more or less massive?
More.
Yeah, more massive. Okay, just wanted to make sure we had these ideas kind of sketched into our minds. So I have a problem for you. Stars are often born in binary star systems. So here's two main sequence stars. It could be in a binary star system. Their colors are shown to you. Different positions are shown to you, where they might be located as they orbit each other and pass in front of each other. I've given you an HBar diagram so you can kind of reason using that information. Here's a plot of the energy received on Earth versus time. And the question says, consider the main sequence stars in the eclipsing binary star system shown in the diagram at right. Which numbered positions correspond with the white boxes in the energy received versus time graph? So I'd like you to not talk to your neighbor. I want you to reason through this by yourself. You got about 30 seconds. Think about it and see which numbers you might come up with for these different boxes. Now, when you go to vote, if you're actually completely unsure of what you're being asked to do, or you don't know how to do the reasoning, you're like, I'm not really sure what's going on here, you can always vote this. And that tells me I'm totally guessing and I'm not quite sure what's going on here. So I'd like you to use a transformation matrix of 1 equals A, 2 equals B, 3 equals C. Which number or letter are you going to put there? That's the one I want you to vote on. What goes there? Which number or letter, in this case, goes there? Should you be voting yet?
No.
Just check it. Okay, let's vote on 3. 1, 2, 3. Oh, that's there. Very interesting. Okay, put your votes down. I'm going to use a technique of peer instruction. Actually, put your votes back up, because you can't lie if your vote's sitting there. I like that. I'd like you to, and by the way, everybody has to vote. I see some of you aren't voting. Could you please put your vote back up? There you go. I'd like you to turn to your neighbor and convince them you're right. You've got about 30 seconds. Just because you have the same answer doesn't mean you're right. So make sure you explain your reasoning. Go. Okay, let's vote again on 3. Let's vote again on 3. 1, 2, 3. Oh, that's pretty good. By the way, the right answer is... Okay, by the way, when I pause, you guys fill in blank. Remember? You're confident, remember? By the way, the right answer is B. Now imagine that having just gone on in your non-science major class. Imagine they were just arguing about the surface temperature, the brightness per unit area, blocking. One's yellow, one's blue. Which one's a loss of more light? Is all of a circle of yellow as much energy as a circle of blue of the same size, but it's blue, it's hot. Imagine that conversation going on amongst your students. This obviously happens late in the semester, where you've covered a lot of background, a lot of different things that they can reason through. Imagine all the pieces you bring to the pie to be able to get there. So I just bring this up. Imagine 1,400 of your future voters having this argument in the classroom. I want to show you a couple other questions. So just help you see how you can have interactive learning be developed around astronomy topics. A new question for you. Remind you that you can vote white if you don't know the answer, or you're unsure of how to do the reasoning, or you think that you don't have a legitimate guess. Before I have anybody vote, can you please grab your cards? Give me an A if you're like, I got some really good astronomy content knowledge. Give me a B if you're like, I don't know a lot about astronomy, because we're in a varied audience here. Let's vote just on that on 3. 1, 2, 3. Okay, it's important that you have somebody who has a strong astronomy background content to talk to about these questions. Okay, I want you to share for that reason. So if you end up, look at the people next to you, show them your votes. If you're both Bs, you might want to switch seats, but if you've got an A next to you, you're in good shape. Okay, so I want to go back to this, and I want to let you all vote in just a second. Afterwards, after the question. Let's vote on 3. Do you need more time?
Yeah.
Okay, let's vote again on 3. 1, 2, 3. Oh, I like all the whites. That's a good time. That's a rainbow. That's good. Again, same instructions. I'd like you to turn to your neighbor. Convince them you're right. Just because you have the same answer doesn't mean you're right. So explain your reasoning. You've got about a minute. Go. And if you have some need for negotiation, I'll be happy to walk around and make you. Now, imagine how big your toolkit, for all you astronomers that are out there, imagine how many pieces you just had to help the people who don't know the content. How much teaching you were just doing. Imagine getting your non-science majors arguing about that buffet of ideas together late in your course. I'm going to let you vote. I have another question for you that's on extrasolar planets. How often have you already said these are trick questions? How often have you already said, damn, these are hard? How many times did you get to plug in numbers to an equation? Never. How often have you used equations as a part of your reasoning? Often. This is part of bridging the gap that we're going to need to think about as we move from bringing astronomy content into teaching and learning about physics. These are some of the basic principles you have to have before you can jump in to some of the higher order reasoning that we're going to talk about that we might be asking students to do. I'm just modeling for you some questions and some examples. Do you guys want to vote on it? Some of you really did really bad. Yeah.
Where are we in this diagram?
Oh, look there.
Oh, there.
It's necessary. And all of a sudden it opens up the problem space for a lot of people. It really does. I mean, there's a whole bunch of things you need to know to be able to solve this problem. You have to have your entire kind of dynamic model of extrasolar planets here. Like, if the star is moving towards you, the planet is moving away. Motion towards you is a positive or a negative recessional velocity. Negative. Can I decompose the problem for you? Yes. I wouldn't normally be doing that in a pure instruction environment. That's what you'd be talking about. You'd be picking apart, oh, I didn't see that part. I didn't see Earth was over there. All of those are the questions designed to be a vehicle for you to have a fully embedded conversation about what we know about this topic area. Not to plug in numbers, not to cancel units. This is much more about, can you even reason about the topic at all? Not can you calculate given a formula. So this is an interesting place to put the learner and us. You're being intellectually challenged by it too. It's not as though this was trivial for you. So I'll just stop there. You can ask questions about luminosity, area, and temperature. What if you're asked to rank the size of each of those places on an HBar diagram when you're not given the size? You're given luminosity and temperature. Another piece of control of variables reasoning that we can easily port into a class in physics that uses astronomical data to be a part of it. We just heard it talk about Hubble plots. Which of these is for, let's try this one actually. Which of these is for a uniformly expanding universe? Which of these is for a uniformly expanding universe? Let's vote on 3. 1, 2, 3. That's pretty good. The right answer is, which of these is for a uniformly contracting universe? Not so trivial anymore, is it? Which of these is for a universe whose expansion rate is increasing over time? Let's go for that one. Which of these is for an expansion rate that's increasing over time? Do you need more time? Some of you are already voting. Let's vote on 3. 1, 2, 3. All of you voting E are wrong. Okay, and we can have a conversation about that, okay? I just want to show you some examples of how to have conversations that involve the dynamics of what we're talking about. I was going to show you an example of animation that uses what we were talking about earlier. This is one that I developed with one of the book publishers, Kevin Lee. If you don't visit UNL, astro.unl.edu while you're here, you've made a grave error, because a resource at your fingertips to start thinking about how to use teaching and learning. Kevin, and in collaboration with many people, myself included, have worked really hard, but his team has developed an amazing number of animations and questions of the type I was just showing you. And it's ever growing. But this is just another example of a simulation where you can change the cluster mass. You have actually control over mass and location of the clusters and where the lensed objects appear in your field of view. It's a great way to start talking about these things. It's dynamic. You can scroll into a scroll bar. You can have everybody make predictions before you do anything, get some skin in the game, talk to each other, make them pee their pants to want to see you drag that scroll bar. Just like many of you want right now to know the answers to these questions. You can get people to actually be hungry for what's going on in your classroom rather than feeling like you're forcing it down their throats. So I just want to then move to, is this stuff successful a little bit? How can interactive learning strategies? Now this data I'm going to show you just happens to be from Astro 101 classrooms, but it's the same and has been shown through physics education research and other disciplines to be just as effective at majors level courses and in courses beyond the introductory level. I'm just going to show you one piece of data that comes from astronomy in a recent study that we published in Physics Today. So the instrument that we were using to measure student learning gain is called the Light and Spectra Concept Inventory. It's one of many concept inventories that exist. We developed this one with one of my students for their PhD project because it deals with central topics that are taught throughout the semester. If Dave's talk showed you one thing, it's that light is the fundamental messenger. And I think even it was also brought up yesterday in Duncan's talk about how that is fundamentally the only sense we have of what's going on in the universe is from what we understand about light. So Doppler shift, luminosity, area, and temperature, Wien's law. It could be just the electromagnetic spectrum of light and its properties. All of these things, types of spectra, Kirchhoff's laws, are all parts of questions enveloped in the Light and Spectra Concept Inventory. So in many ways, it captures a fundamental chunk of what you teach when you teach a semester of astronomy. This study involved 4,000 students from all over the country with 31 different institutions, 36 different instructors, 69 different class sections, which range from as small as 10 to now as big as 750. Our data's in this now. They were from all over the country. And I need to make a really important point here. They sampled all types of colleges, 2-year colleges all the way to 4-year research institutions. And everybody in the study had been through one or more of the professional development workshops that we offer through the CAE. So I want to bring this up because they were all drawing from the same experiences and how to change their classroom, pulling from the same tools in making kind of their version of an interactive astronomy classroom. So they'd all been through the workshop series that we run. And if you want to know more about teaching astronomy and how it might be a vehicle for your physics class, come to the workshop. It will bury you in 2 days, 16 hours of boot camp about different interactive teaching methods that you could bring to your physics classrooms. This is data from physics, actually. How many of you are familiar with the Higgs study? Just a quick show of hands, Higgs study? Well, that's quite a few of you. This is a replotting of the Higgs data with normalized gain, which is a metric which tries to estimate of the percent of questions you got wrong on day one, how many of those did you get right, or what percentage did you gain after instruction has occurred? So it's a normalized gain. The blue dots in this case are the interactive classrooms, and the pinkish colored dots are the traditional engagement classrooms. This study was done a decade plus ago, and it was really valuable because for physics, it opened the can of conversation about, hey, look, it's pretty obvious that the interactive classrooms are doing quite a bit better than traditional. This really started a big conversational agent. In astronomy, we did not have such a study done yet. So one of my first goals was to develop curriculum that could be research validated in our classrooms that we teach at Arizona, develop a workshop program so a bunch of professors had started using them in their classrooms and had some experience, get a survey instrument that could be validated that everybody could use in their classroom, and then do a national study. So that was physics version. This is astronomy data. The boxes provided to show you where the physics data would be if plotted on the same graph. Does it look the same? This is you can use your voices to interact with it. Does the data look the same? No. Okay. In the physics case, would you say that the pretest scores were narrowly band or broad?
Broad.
Yeah, they're wide range. In fact, there's classes. Every dot on here is a class, not a person. There were classes that were nearly 70% right on the pretest. This is I am a exclusive college with students who took AP Physics for 3 years, and we know a lot of this on day one. Did having a high pretest score determine whether or not they would have large gains or not? Not at all. That's why normalized gain is an interesting metric at some level, because of how much did you get based on where you started. Would you say that the physics or the astronomy data illustrates that there's a bunch of students who took AP astronomy before they came to college? Also keep in mind these are a lot of non-science majors. About 80% of this class is non-science majors, only 20% science majors. So is there a difference amongst the different types of colleges, or are all colleges about even? That was about one person. Thank you, Duncan, for playing. I really appreciate that. Maybe the rest of you can come on board with this, okay? This is part of the interactive instruction is I'll kick your ass out if you're not part of it. Okay? Let's try that again. Would you say that the type of institution you're at determines your initial value?
No.
Yeah. No. Does it determine your gain?
No.
I think if you watch for a little while here, you'll see all kinds of dots up here. One type of institution does not dominate. So it's kind of an interesting thing. Class size.
One diamond below that and 6 diamonds.
There are more than one diamond down here, you just might not see them all. There are more than one diamond down there. And would that be causal? It is interesting if that were true. How about class size? Does it seem like a deterministic variable?
No.
Exactly. And I would bring this up to say this is based on how people learn. And that is independent of whether the class has 20 or 200 and whether or not it's taught at a community college or a four-year R1 institution. It has a lot more to do with the curriculum and the instructor's use of that curriculum and their implementation in their classroom. This is actually statistically pretty insignificant. If you do a test on it, it's a very small number statistic class. That's one of the problems. So you can see they're another 25. Yeah, it's actually more 0 than negative, if you want to treat it that way. We also asked every professor to fill out a survey which told us how many hours a day do you use interactive, or how many minutes out of the semester, if you will, do you use interactive learning strategies? By plotting how many days do you teach, how many hours in a day, do you do exams, do you have a recitation section, what are you using, how much time do you give students to use, think, pair, share, peer instruction, tutorials, ranking tasks, and we calculated a metric, which is your percent of the semester taught interactively versus gain. So this is now percent of class time taught interactively versus gain. I know it looks like a hell of a lot, but I've never drawn a line through it. Might not be as bold as but I do want to draw attention to the line that was drawn in the previous plot and in Haig's plot was the 0.3 gain line. It was kind of established as this is the threshold where traditional lecture courses don't seem to cross this line. So I just plot that on this graph. You also see that no class crosses that line until they're 25% interactive or more. But the more important and take-home message is just because you're more than 25% interactive doesn't ensure a damn thing. And that's the interesting part. Here's somebody who's 50% of their time using interactive teaching methods, and their gains are relatively small. We matter as much, if not more, in determining where you end up on the spot. And by we, I mean you, the individual who walks into the classroom and what you do with the tools you're given. So as we sit here and talk about how to move from one topic to another and bring astronomy's beauty and inspiration and as a vehicle into the classroom, and we sit here and we think, maybe we should make a textbook, maybe we should have some new problems at the end of each chapter, and ... I want you to really stop to think about how important professional development of faculty is going to be. Because who brings it in the classroom and what they do to create an instructional environment that is valid and useful for their students is the most powerful data in here. There's 2 professors in this data, in this area here, who teach at the same university. They teach 1 hour apart. They have the same TAs back to back. They have the same lecture slides, homework, exams. They're identical courses except for the professors. 1 hour after the other, one leaves and another comes in. They work together. They know the curriculum very well. They both have the same PCK, if you will, but their gains differ by 0.2. Huge difference. Because one of them doesn't interact with class. One of them hasn't taken the time to help the students understand why they're doing what they're doing in class. One of them doesn't emphasize that you need to fill in the blank when I pause if you don't. They just let everybody slide. And the students go along for the ride. Your innate ability to teach is part of this. And we need to do a better job as a nation. Major, ethnicity, parents' income, language, math preparation, all sorts of different variables to describe a student population. And we created a multivariable analysis methodology to try to find out how much of that variance in gain could be described by students' individual characteristics. This is the data. I'm not intended for you to be able to read this. I'll give you some insight. Men did a little better than women overall on gain score. Higher GPA students did a little better than low GPA students. These are not astonishing things that haven't been seen before. The only major that has statistically higher gains, and it was a very high statistical significance, was arts, humanities, and social sciences. They outscored the science and technology majors by a significant amount. Because the class is based on discourse, because it doesn't rely on you to plug and chug, your toolkit just got taken away from your science majors. Can you critically reason in words? Your ability to write and speak about what you understand is a great indicator of your actual understanding of it. Your ability to plug and chug is a mask often for your ability to communicate it to somebody else. And that's an interesting thing. Arts and humanities and social science students talk to each other. That's what their discourse is based on, language use. The single most important variable in this coupled 13 and 15 variable model was interactivity score. It increased the explanatory power of the model by 30%. So choosing to use interactive learning strategies is the most powerful variable, rather than worrying about all the differences amongst your students' population. And then one last thing, we coupled the interactivity variable with every ascribed characteristic of student. Males and females versus interactivity, high and low achieving versus interactivity. And it positively correlates with every variable. So no one's being left out by using interactive learning strategies. And there was no group that biased to interactivity. It helped equally men and women. It helped equally high and low achieving math scored students. It helped equally high and low GPA, ethnic background, languages. So it is about how people learn. And interactive strategies have that promise. I think I'm probably out of time, but I'm not sure.
Yeah.
Yeah? Okay.
I'd like to have a question.
Yeah. I'll just stop here.
Thank you.
Yeah.